Hello, everyone. Welcome to our third workshop of EcoHacks. We are really excited to have you guys here today for our machine learning workshop. And for machine learning, today we have, I guess you can call it guest speaker. Vishnu will be giving us an introduction on artificial intelligence. And yeah, so let's get started. So I'll pass off the mic to Vishnu and he can get started.
All right. Yeah. Hello, everyone. Today, I guess we'll be doing a sort of machine learning workshop. So I'll start by sort of giving an introduction to the concept of artificial intelligence and some different ways to implement it. So firstly, I guess I'll talk about AppDev League. So AppDev League is a 501c3 nonprofit organization, which is dedicated to helping underprivileged students learn about computer programming. We post educational YouTube videos, host hackathons, and are currently developing an educational platform to help students learn computer science. And if you're interested in joining our team or just seeing more of what we do, you can check out our website at appdevleague.org. So yeah, without further ado, let's start learning about artificial intelligence. So in this first part of the workshop, we'll learn some general information about artificial intelligence and machine learning. So like what exactly artificial intelligence is, why we generally use Python to code for it, what machine learning is, as well as the process that machine learning networks actually use to learn. And we'll be looking at two different basic frameworks of learning here in this first part of the workshop, which are supervised and unsupervised learning. So artificial intelligence is a really expansive, large field covering many different disciplines, which range from computer vision to machine learning. And it aims to simulate parts of human intelligence and human decision-making in computers using some mathematical models. There's a lot of applications of artificial intelligence in finance, housework, and scientific research. And some modern examples include voice assistants, self-driving cars, and AI chatbots. Python's useful for artificial intelligence for many reasons, but some of them are that you don't need to write as much code because there's a lot of convenient predefined libraries that you can use to implement machine learning networks, like, for example, TensorFlow and PyTorch. There's also a lot of community support for Python, so it's easier to resolve any issues you run into by just like asking the community for help. And it's also easy to learn Python and interpret what code actually means because Python was created in a way to make it very similar to English in its syntax and structure. And this makes it easier to interpret what exactly code in Python is doing. Now, machine learning is a subfield of artificial intelligence, and it basically sort of relates to machines learning tasks without being explicitly programmed for those tasks. And it does this by aiming to replicate human learning patterns in order to actually find patterns in data or like learn how to do a task more efficiently and effectively. So instead of, in artificial intelligence, you might just, for example, code some robot to like go left and then go right multiple times if you want it to try and move around a room or something. But with machine learning, you can actually sort of navigate any sort of path without having to pre-program it in directly beforehand. Deep learning is a more complex subset of machine learning where machines actually create models that help them identify patterns easier. So it's almost like a machine learning model for machine learning in that sense. So machine learning models are trained on data and they're tested on data that they haven't seen yet to evaluate their effectiveness. So models start by first gathering and pre-processing data into a format that's easier for them to find patterns in. You then take a separate training and testing set, and this is because you want to be able to give your model a data set for it to actually learn patterns from, but you also want data that they haven't seen before in order to get an unbiased, reading of how effective the model is in scenarios that it hasn't encountered. After that, you choose a method or a framework to build your model with, and then you build that model. You then train the model on your training set of data and finally test it on the testing set to see its effectiveness. So models are like the actual programs that do tasks in machine learning. And the type of model that you use depends on the task. So there's different frameworks, sort of like convolutional neural networks, recurrent neural networks, or other things that are better suited for certain tasks than others. And as you continue learning more about machine learning and artificial intelligence, you'll be able to recognize those different models. And a lot of testing and application is required to figure out the best method or model to use for a given problem. So now let's look at some machine learning algorithms. So first, we have supervised learning. So supervised learning is when a machine learning model is fed labeled training data. So labeled training data means that along with the data that's given, the machine learning model is also given the classification of the data. So say we're trying to create like a classifier that splits these polygons into squares and triangles. So in a supervised algorithm, you feed it labeled training data. So you can see all of the squares have been sent in along with the label square, and all of the triangles have been sent in with the label triangle. And this means that the machine learning model knows that all of the squares are squares and that all of the triangles are triangles. And what it does is it finds patterns that relate all of the squares to each other and relate all of the triangles to each other. So say it finds out that squares have 4 different vertices, whereas triangles have 3 different vertices after that. You then test it by passing in unlabeled testing data after the training, and the algorithm generates a label for that unlabeled data. So here we're given a figure that has 4 vertices. So if our machine learning model was sort of figured out that squares have 4 vertices and triangles have 3, it would label this as a square, which is what it does. And if this testing is successful, we can use the model to predict unknown labels. Some different types of supervised learning algorithms we'll go into a bit more detail later in the workshop, but some of them include linear regression, which is using a line of best fit to predict future values of a variable, logistic regression, where 2 classes are fitted using a logistic curve, decision trees, which are sort of yes-no trees that make predictions, and neural networks, which are complex mathematical models constructed using nodes and weights, which is something else we'll also be covering later in the workshop. There's also unsupervised learning, where unlabeled training data is fed into the algorithm. And what the algorithm tries to do is it tries to actually classify them based on distinguishing characteristics. So the algorithm learns and finds a hidden pattern in the data. So like, for example, let's just say that the model, again, identifies that some of these figures have 4 vertices and some of them have 3 vertices. So it splits them based on the amount of vertices that the figures have. It then outputs the classified inputs. So unsupervised learning typically is used to find hidden patterns in data that are invisible to humans. So say we didn't know if these things were different at all. We could use an unsupervised learning algorithm to try and see if there's different sort of subclasses within this data that we can identify. And the results are sometimes run through experts to make sure that the pattern found actually exists. And once again, just like supervised learning algorithms, if the pattern does exist, then the model can be used to, diagnose or try and classify unlabeled inputs as well. So some applications of unsupervised learning are categorizing news articles automatically based on different classes, recognizing objects and images. So if an unsupervised learning model doesn't necessarily know what the object specifically is, but if it can recognize that's different from the background, it can recognize the object. They're also used in medical diagnoses, finding anomalies in data sets, and discovering data trends for recommendation. So again, a lot of these are sort of finding a hidden pattern in the different types of articles or different types of classes and actually classifying them. So yeah, there's a lot of really cool intro to machine learning websites and games. Some of them include Google Quick Draw, which is a machine learning model that identifies what type of image you're drawing. It asks you to draw a specific type of object, like a helicopter or something, and it tries to identify the object that you draw. And this is a supervised training algorithm that use different labeled images and drawn figures to sort of identify the defining characteristics of different objects. So that's really fun. There's also the TensorFlow Playground, which allows you to design your own neural network to classify these different colored dots. And finally, there's Google Teachable Machine, which also allows you to create your own models to sort of find trends in photos, which is also really nice. So I guess I can pass it off to Joshua to talk a little bit more in depth about the different types of neural network frameworks.
Yeah, thanks so much, Vishnu. That was a pretty informative introduction to machine learning. So does anyone have any questions for Vishnu here? You can feel free to put it in the chat. All right, so if there's not any questions, I guess I can get started on my portion of the slides. So it's waiting for it to load. Yeah, can you guys see my screen right now?
Yeah, we can see it.
Yes.
Right, sounds cool. Yeah, so I know that Vishnu described a lot of different machine learning topics and algorithms. So in I guess the second part of the workshop, we'll go more in depth on the algorithms and I guess the theoretical part. So you guys can have a better understanding of actually how the algorithms work. Yeah, and at the end of the workshop, we're going to be doing a live demonstration. Vishnu will be doing a live demonstration to show you guys actually how to implement these algorithms and methods. All right, so let's get started on our second part. So I'll be talking about algorithms in depth. All right, so I know that Vishnu discussed that there's like two major types of learning, although there are also like other types of learning, but we'll only be talking about supervised learning and unsupervised learning in this workshop, since these two are probably the biggest ones. So yeah, in supervised learning, there are basically two types of supervised learning. So there's classification and regression. So classification is basically an algorithm that separates the data into each one category or not. So this is a good example. So let's look at this picture right here. Is this picture a tree or not? So this is basically a kind of a good example of what binary classification is. It's basically like a yes/no question. So you'll have a bunch of data, that tree data, and you'll be inputting it into your algorithm, and your algorithm should be able to output next time when you test it, if the picture is a tree or not. And one example of classification is logistic regression, which we'll be going more in depth soon in this presentation. So yeah, our second type is regression. So regression is the algorithm that predicts output values from the input. And one example of regression is linear regression. So don't get confused, guys. Logistic regression is actually not considered a regression algorithm. It's actually classification. And we have a good example here for regression. So let's think about housing prices, right? Let's say we have an independent variable and the dependent variable will be the price of the house. So let's say the independent variable is the size of the house and the dependent variable is the price of the house. So we want to make an algorithm that is able to basically kind of plot a line or output an equation that's able to kind of predict the price of the house when you're given the size of the house. So yeah. Right. Sorry, guys. I think I mixed up the slides a little bit, but we're going to go back to k-means in a bit. This is actually not the supervised learning. So our first supervised learning algorithm I just mentioned is linear regression, right? So this is actually the regression algorithm that we were talking about. So let's go more in depth on what actually linear regression is. So this algorithm actually models a target prediction value based on an independent variable. So as I said before, we're just basically trying to create a line or basically find a y equals mx plus b that can be able to predict the output. And there are multiple libraries that you can use in Python specifically that can automatically do this for you. So you don't actually have to manually do linear regression. Some of them includes scikit-learn. But in this presentation, I kind of want to explain to you guys actually how linear regression works behind the scenes, since that is a pretty important topic But basically in practical uses, you won't actually be coding up the algorithm. You would just probably be using a pre-built library or package. So yeah, let's go back to the scenario. Let's say you want to buy a house, right? But you want to be able to predict how expensive a house is based on different parameters. So I know that I gave a parameter earlier. It was the size of the house, but you can also do a multivariable linear regression. So we can include multiple parameters like the size of the bathrooms, number of bathrooms, size of rooms, number of rooms, size of house, and yeah, other like including location too as well. And we want to see how these parameters are actually affecting the price of the house. So that is kind of just basically what linear regression is trying to solve here. All right, so let's look at linear regression behind the scenes a little bit. Don't be overwhelmed by these equations. I'll be explaining them real quick. It shouldn't be too hard to understand. So basically we have a hypothesis, which is basically, you can consider it as the y equals mx plus b line, or like the line we're trying to predict the values in. And for multivariable linear regression, we'll have basically the hypothesis of x is equal to theta transpose x. So the theta is actually the coefficient of that variable. So you can think of it as the m in the y equals mx plus b. And we have this transpose sign since most of the times in machine learning, you'll be using actually matrices instead of actually manually using for loops. Since matrices, matrix multiplication is often very efficient and easier to use. But if we spread this out, it'll basically just be theta of 0 times x0 plus theta 1 x1, theta 2 x2, and so on. So yeah, so x are the parameters. So as discussed before, size of the house, how many bathrooms, how many rooms. Yeah, so we can have an infinite amount of x. And as I discussed, the parameters coefficients are the theta. And yeah, I have said here n is equal to the number of features. Features is basically the number of parameters, basically. And we have here that m is the total training data. Let's discuss a little bit about the cost function, actually. So the cost function is basically seeing how close your prediction of, let's just say the hypothesis of the hypothesis you created throughout the algorithm is compared to the actual data. So this is the cost function. We'll be basically taking the difference and squaring them, and we will be summing them. So this is a way to actually see the cost function. So in the sense that if the cost function is really big, like 1 million, that means that our line or our hypothesis is really bad. But if it's like close to like 0, then it means it's really good. All right. So yeah, this is a good demonstration also. We'll also have to be using gradient descent. So this is, as you guys know, back propagation. So basically, we would want to basically lower the cost, right? How are we going to minimize the cost of our cost function? So if you guys look here, we have a picture of a cost function. We have weight in the bottom. This is irrelevant to our house example, but you guys can see basically if we have a cost function like a quadratic curve, we would want to make it so that the cost reaches the minimum point, right? So this is basically what gradient descent is trying to do. And we'll be discussing the formula a little bit later, but as you can see in this picture here, this is basically the same thing as this picture here, except it's in 3D. So this one is basically when there's one parameter, and this is when there's two parameters. And this could be infinite, but it's hard for us to actually visualize what gradient descent looks like after it's like 2 parameters. But yeah, so basically, if you look in this curve, we have this graph right here. You guys might be familiar with this graph. It's often used to like, it often is used on like Google Maps and that kind of stuff. So the red one, the red like shade basically means that it's a higher elevation, and the blue one basically means lower elevation. So we want to reach the lowest elevation, which is basically reaching the minimum cost of our cost function. So as you guys can see, this is basically the ideal path that we have to trace out. All right, cool. And yeah, so this is actually the formula of how we're going to actually be using gradient descent. So we'll be changing basically the coefficients of the parameters of all the parameters simultaneously, which is basically, let's see if I can go back, which is basically giving us this path all the way down to the minimum cost. And this derivation is involves some calculus. So if you guys don't know calculus, you guys can just take in this formula, but basically we're just trying to find a derivative. Let's see if I can, oops. Trying to find a derivative of the cost function and basically moving it down until the derivative is 0, which is basically when the minimum cost is minimum, right? And yeah, this is another picture of the graphs we discussed earlier. We're just basically trying to reach the blue part or the lowest part, which is basically the minimum cost of the linear regression. And that way we'll get a good prediction or a good hypothesis for our housing problem. All right, so let's talk about logistic regression. So this is, as I said before, a classification problem. This is actually not regression. So same example, if you are given this picture, is this a tree or is this not a tree? This is basically binary classification. Well, we want to see if it is a tree or not a tree. And yeah, don't get fooled by the name. It's not a regression algorithm. And same thing with linear regression, different libraries and packages like skikit-learn. You can directly perform logistic regression in one line. So you guys don't actually have to like perform all of these like gradient descent, these formulas, but it's a good idea to actually know how it works behind the scenes. So you guys can.
Yeah, Joshua, just quick, we have a question from the chat. Is the gradient descent formula the same when the number of parameters is increased?
Let me see. Okay. There's a lot of questions. Okay, so yeah, is the gradient descent formula the same when the number of parameters increase? Yes, it is the same. As you guys can see here, we want to perform gradient descent from all of our parameter coefficients from j equals to 0 to n. So this is basically all our parameters. So it should be the same. So let's say we have 2 parameters, then we will have theta of 1 is equal to theta 1 minus alpha, blah, 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 blah. And in the next line, we'll be doing theta of 2, blah, 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 blah. So yeah, it's kind of you can think of it as like a for loop. And also I forgot to discuss, but this alpha here is actually the learning rate. So it'll be pretty important in actually determining a good learning rate so that the gradient descent works and we reach the minimum cost. So if the learning rate is too big, the point here might just like zigzag and never converge at the minimum point. So this requires some fine tuning and some experiment depending on the problem you're trying to solve. I hope that answers your question. Yeah, I'll be keeping the chat open to see if you guys have other questions. All right, sounds good. So let's get back to logistic regression. Where do we leave off? Yeah, so these different libraries and packages can be used directly to perform logistic regression. So you won't actually have to be implementing a logistic regression. You'll just be calling some method. All right, so logistic regression is really similar to linear regression, except that we want the program to output yes, no, right? So in this case, we'll be outputting 1 or 0. So we don't want the housing price like curve. So we won't be like outputting like 15,000, 1 million, 2 million, 3 million. We just want a yes or no. So in order for us to achieve that, we will actually have to be putting our hypothesis through activation function. So there are multiple activation functions you can use, but for the purposes of our workshop today, we'll be using the sigmoid function. So the sigmoid function is 1 over 1 plus e to the power of negative x. So you guys might be wondering why this sigmoid function is actually good. As you can see, the sigmoid function is graphed down here. And you can see that basically as x approaches infinity, we are getting an output of 1. And if x approaches of negative infinity, we're outputting 0. So this is a good function since basically all the inputs we put in, the sigmoid function will be basically giving us a number of 0 or 1. And this is basically what we want for logistic regression. All right, yeah, like linear regression, we have a hypothesis equation. Sorry guys, this kind of I guess I was using h of x, but now we're using z. This is basically the same thing, but just another different types of variables, but it represents the same thing. So as before, same thing, hypothesis is equal to W transpose X plus B. So W transpose X is, let me move this back. It's basically the same thing as theta transpose X, right? It's the coefficient of each parameter. And yeah, here we have, as you can see, we have the hypothesis in the first line here. But after that, we're going to be putting into our activation function, which in this case, we'll be using sigmoid function. So we'll be getting the output of A variable. And yeah, so our cost function or loss function. So cost function is basically the same thing as loss function. It's actually kind of different from what we discussed earlier, right? So if we go back, the cost function is this summation of the difference. But the thing is, we can't actually use that since we want to find a cost function of the actual value, which is 1 or 0, which will be inputting, right, to test. So we would want to find a loss function of closest to 1 or closest to 0. So this is our loss function. There is calculus proof, but that'll be out of scope for our workshop today. If you guys are interested, you can definitely research this online and see why this actually works. But in the next slide, I think I'll be discussing, a little bit kind of a proof, but not really a proof. This is kind of just like intuition on why this works. So like before, we had a cost function of this is basically the same thing, right? So hypothesis and our actual y, and we have to summate it, and then we divide it by m. So why does this actually work? So we made it so that our cost function, when y is equal to 0, is equal to negative log. And then when y is equal to 0, we made it negative log 1 minus hypothesis. So the reason why we did that and why our loss function is kind of like this huge like formula with logs inside is because if you can see in the graph here, if y is equal to 1, right, this curve goes down. So this is h of x, and then I think the y axis is the cost function. So the closer our hypothesis gets to 1, we would want to reward that behavior, right? So our cost will be closer to 0. But the thing is, we can't actually just only use one graph, because let's say is y is equal to 0 and we use the first graph. This does not become valid, since if h of our hypothesis gives us 0, then our cost function is really high, which doesn't really make sense, right? Since we want to reward our algorithm of giving us the right value. So this is why we have another graph here. When y equals 0, so we have the function of negative log 1 minus hypothesis. And this makes sense now, right? So when the hypothesis gives us 0, when y equals 0, so y is our target value, which is like the data we want to actually hit with our hypothesis. So when hypothesis actually gives us 0, the cost function is 0, which gives us the correct cost function. So we'll basically have, in a sense, 2 cost functions. But if you want to combine them into one equation, we can also do it like this. In this way, where we separate the cost function into 2 parts for if statements. But if you want to combine them, if you want to combine them, definitely we can use this equation. And there'll be a further mathematical proof that which we will not be going over on why that actually works. All right, so we have a question in the chat on, do we get access to the Google Slides? So we're planning to be, we're already recording this lecture, and we are planning to upload this on YouTube. I'm not sure if we are actually gonna upload the slides. So depending on the amount of interest, I might be able to upload the slides for you guys. All right, so let's get to our third algorithm we have today. So neural networks. This is probably an algorithm you guys have heard of, and this is probably one of the most powerful machine learning algorithm there is. So you guys might be wondering, is neural network supervised or unsupervised? So technically, neural networks can be supervised and unsupervised, but for the purpose of our workshop today, we'll be just only going over supervised. So we'll be putting in labeled data instead of unlabeled data. So yeah. So what are neural networks? So neural networks are computing systems inspired by our biological neural networks. So the neurons in our brain is kind of basically formatted like how we actually develop the algorithm from. And this solves, yeah, as I said, supervised and unsupervised problems, but we'll be focusing on supervised. So some benefits of using neural networks like to solve problems include face recognition, AI-generated music, and image generation. So like, how do we know that, as for example, like if you have an iPhone or any other phone that has face recognition, how does your phone know that it's actually you and not someone else? So it'll be actually using neural networks to solve this question. So linear regression and logistic regression is not powerful enough to be able to solve these questions. All right, so let's look at let's look at the brief introduction on neural networks and what it actually does. So it's kind of like, as we discussed linear regression and logistic regression, we have a hypothesis. In this case, it will be using Z, right? And we will have W transpose X plus B. But the different thing is we actually have multiple neurons in our neural network. So it's not just one neuron here. This is like similar to logistic regression here, right? So we have one neuron. But in neural networks, we have a bunch of neurons that we are basically trying to alter each of its weight, activation function, and everything. And then, oh yeah, I didn't explain here, but our input layer is basically where we input all our values. So I guess for the tree example, we'd be inputting our tree images here, and there'll be hidden layers throughout our neural network. The hidden layers, depending on your problem, there can be 1, 2, 3, and 2 as much as you want. But for now, we'll be using only one hidden layer as a shallow neural network, since as we delve into more hidden layers, it gets way more complicated. And lastly, our output layer is where we will be outputting our results on, let's say, if that is a tree, right? We will be outputting 1. If it's not a tree, we'll be outputting 0. All right, yes. Yeah, don't worry, guys. This is a lot of theory for you guys to take in, but we'll be demonstrating on actually how to use this in real applications and maybe in your EcoHacks project. Yeah. What do the hidden layers contain? Okay, that's a good question. The hidden layers, like every other layers, contains neurons. So for example, in our logistic regression, right, we are trying to basically output a 0 or 1. But in neural network, we're basically having a bunch of 0 or 1s. So basically outputting a lot. And we're basically trying to just change the connections, or in this case, it's called weights, right? The connections between each node to give us an optimal algorithm that gives us the results that we want. Does that answer your question? All of these are basically neurons in a sense. Yeah. All right, so we have more math here. Unfortunately, this is basically a lot of theory, but it's important for you guys to actually understand how neural networks work. I know there are basically a lot of different libraries like PyTorch, TensorFlow that you can basically just have like one function and it kind of just does everything for you. But so let's look at this diagram here. So as I said before, we have like three axes in this case. So basically 3 parameters. And you guys can think of these arrows as like we discussed before, theta, right? So when y equals mx plus b, m is a coefficient. So you guys can think of this arrows as the coefficient of the equation we're trying to find. And A1, A2, A3, A4 are basically the outputs. And yeah, so the subscript is giving us the number of the output, and we have a superscript here with the brackets around that is indicating our layers. So normally we call the first hidden layer layer 1. All right, so we have 4 equations here for our example here. This might look really familiar, right? This is basically kind of the same thing as we discussed before on logistic regression and linear regression. I guess more similar to logistic regression since we're actually putting the hypothesis value into our activation function here, or we're using sigmoid on this one. Yeah. So Z1 of the first layer, these equations are all for our first hidden layer. that's equal to W1 layer 1 transpose X plus B1 first layer. And we're going to be inputting that into our sigmoid function, which will give us the value that we want. And we'll put that back into the neuron that we are actually outputting. So for A1 is basically this neuron, A2, A3, A4. So, all right. Okay. So I can repeat a little bit. For W1, it's basically all of these arrows that are pointing from any of these X1, X2, X3 to our first neuron we have here in our first hidden layer. Right. Okay. Sounds good. All right. So let's look at the neural network cost function and gradient descent. So the neural network cost function and gradient descent definitely gets a little bit more complicated since we don't have like what we did before, like logistic regression. We only have one neuron. We have multiple neurons here. So this is really similar to our logistic regression equation actually, except we have another summation here. The reason for the summation is, so if we just consider like one neuron here, sorry, if we consider one neuron here, like if we just ignore A2, A3, A4, this is basically just like kind of like logistic regression, right? But now we have A2, A3, A4. So that's why we need another summation sign iterating from 1 equal, oh, my bad. K is equal to 1 to K. So M is the number of training examples that we're giving into this neural network. So yeah, this equation is really similar. And for our gradient descent, it is kind of the same thing, right? We are basically, we're basically trying to, if you guys remember, if we have a curve, we're trying to find a derivative and we're trying to make it so that the cost function goes all the way to the minimum point, which is basically when we minimize the error. So we're basically comparing on, I guess, the values we have here. For our values we have to train and the values, actual value, which is basically, we're just comparing if the actual value is the same as the value we're outputting here, which is y hat here. Yeah, so neural networks actually gets really complicated into the math. So this gradient descent formula looks pretty simple, but if you're actually trying to take the partial derivative of each parameter here of this gigantic cost function, we'll get basically these types of formulas. So dz, dw, db, dz, dw, db. You guys might be wondering what this is. So remember, z is basically our hypothesis, w is our weight, and b is our bias. So the y equals mx plus b, that b is our b. So for these derivatives, these are actually all partial derivatives. It's just we're just simplifying the form so it looks more cleaner here. So in reality, dz will be the partial derivative of the cost function with respect to z. Yeah, so basically, once we, these formulas, I guess you can just take it for now. I wouldn't worry too much if you guys don't actually understand this. There's a lot of math and theory that goes into it. But basically, once we get these formulas, we can plug, like for example, dz, we can plug this back into the gradient descent formula in place of this partial derivative, and we'll basically be performing gradient descent on our output value, which is in our second layer here. So yeah, you guys, I think I discussed all these variables. I guess G might be a little bit different. I'm sorry, I didn't keep the variables consistent in this lecture, but G is basically our activation function, which we were using as sigmoid. Yeah, so don't worry too much if you guys don't really understand this. This is not necessary for you to use gradient descent. And also the other part, I guess the right part is more talking about the gradient descent of neural networks with multiple training examples. So like if we have a file of XY coordinates, the left part is only for one XY coordinate and the right part is for all the XY coordinates. All right. So yeah, let's go back to unsupervised learning. Yeah, accidentally copied, I think, the slide in the front of the presentation. I'll be deleting that later. So unsupervised learning, as Vishnu said earlier, it's basically putting unlabeled training data into our algorithm, and we're hoping that the algorithm somehow like kind of groups up our data and gives us an output. And neural networks can do unsupervised data learning, but we'll be not covering that today. And the main algorithm we'll be covering, or basically giving an example of what unsupervised learning looks like, is the k-means algorithm. So as you guys can see here, this is basically a brief differentiation of unsupervised vs supervised learning. So supervised learning, we're just trying to find, the a good hypothesis that lines up with our data. And unsupervised learning is basically, we're just giving a bunch of unlabeled data and we want the machine to somehow figure out any patterns or group them up. All right, so let's look at what k-means algorithm is. So this algorithm is, as I guess you can call it a clustering algorithm. So let's look at this picture right here. It's a really good example of actually what we want. So we have a bunch of green dots. So these green dots are all of our unlabeled training data. And we want to find a way that we can actually group them up, right? So if we look at it as humans, right, it's pretty obvious. We have one group here and we have one group here. But this is less obvious definitely for the computer and the machine. So we want to find a way for the machine to actually differentiate these two groups of green dots. All right. So yeah, we'll basically be choosing the number of seeds we want. So in this case, we have 2 seeds. So we have 2 centroids here. And it doesn't matter where the centroid is, since this is the first step. So let's just have one centroid here and one centroid here. And then after that, we will be looping through all of these green dots, and then computing the distance of the green dots to these 2 centroids. And then we'll be basically labeling them, or in this case of the picture, we'll be coloring them depending on which centroid is closest to them. So let's look at these points, right? These points here, it's obviously closer to this centroid rather than this centroid. And let's look at these points here. These points here are obviously closer to this centroid as compared to the red centroid. Okay. So basically, we are kind of separating this into, I guess you could think of 2 halves. So after you have done that, we'll be basically, same thing, we'll be, I guess not same thing, but we'll be looping through these 2 groups, these red dots and blue dots, and then we'll be adding all these X components in this case and Y components, and we'll be kind of finding like an average of all these points. So the average in this red group here is around here, and then we'll be putting our red centroid all the way there. And same thing applies to the blue group. We'll be finding the sum of the blue groups, and we divide it by the number of blue dots, and we find the average, or the center of all these points, added together and divided by the number. So as you guys can see here in picture D here, basically we have these centroids in the middle of all of these 2 groups of data. And then basically the same thing applies as what we did in C. We'll be doing the same thing. We'll be looping through all these dots and comparing them on which is closer. Is it closer to this X, red X, or is it closer to the blue X? And we'll keep doing this until basically we are satisfied, or there's some exiting condition that you'll be putting in, and then we'll be outputting it as here. So as you can see in picture F, we have a pretty good representation of what the robot would do, and it does pretty well, right? Grouping these two groups. So yeah, the slide basically kind of explains it. I was kind of explaining it intuitively, but I guess we can go in more in the math. So we compute the sum of the squared distance between data points and all centroids, like I said, and we assign each data point to the closest cluster or centroid. And then we compute the centroids for the cluster by taking the average of all the data points that belong in the cluster. And I put a picture here as the mathematical formula for representing this algorithm. But I feel like the intuitive explanation is way better to understand than just looking at the math formula. But if you guys are interested, this is the math formula here. And yeah, so we have mu here, which is basically the centroid, if I didn't mention it before. All right. Yeah, so that will be it about our deep dive in algorithms. Obviously, there are way more algorithms in machine learning, but these are some of the, I guess, the intro algorithms for you guys, maybe to actually get familiar with and understand. And yeah, thanks for listening. Feel free to ask any questions in the chat right now, but we are not done yet. I'll be handing off the microphone to Vishnu. He'll be giving us a live demonstration on actually using these topics and actually how to implement this in real programs.
All right. Yeah, let me just get my screen share up. All right, so I guess we can start by looking at an actual example of like a fully coded neural network. So this here is a neural network that's trained to classify images from the MNIST database. So basically what MNIST is a set of human handwritten numbers that is standardized. It's just like a really standard thing that used to train neural networks on. And it's a set of handwritten numbers, and the goal is to classify these handwritten numbers as like 1 or 2 or 3 or something. Like you just want to classify the number from the image. So you can see here, we start by, this one uses PyTorch. So we start by importing PyTorch and NumPy, which are both really useful for, coding machine learning models. This section isn't as important. It's just downloading the images from the data set. And then we can use a library called matplotlib to actually visualize the data. So this part's not as relevant to the machine learning, but you can see that the MNIST dataset has these images of handwritten numbers and labels that show like what the number actually is. So if we create a neural network model to train it on MNIST, we'll be creating a supervised model because each of the images has a label on it. So you can see this is one batch of 20 images from the training data set. And this just like zooms in on one of the images and shows like the pixel color values for each of these. So the first thing to notice is that this image is a 28 by 28 square of pixels. So when you define a neural network, you have to take in 784 input values in order to actually process this image using the neural network. So here you can see we're just implementing some of the neural network relevant libraries from PyTorch. So this NN, like Joshua was saying, there's like some pre-built methods of implementing neural network layers instead of like using the full math and like hard coding it yourself. And this is a way to create a simple neural network using PyTorch using this NN module. So you can see NN.linear is like the same type of nodes that we've been discussing before, where there's a weight and a bias that are used to calculate the output of the node. And there's a lot of different hidden layers as well to sort of increase the processing power of the neural network. So you can see we start with 28 times 28 because this thing is 28 by 28 pixels. So there's 28 by 28 data values. And we sort of just slowly reduce the number of hidden nodes until we get down to the 10 output nodes that we have. And these 10 output nodes represent each of the digits from 0 to 9, because when we eventually train this network, we're going to want to be able to actually see what digit it is. And we'll be using those output nodes to, actually display the result that's generated by the network as well. Now, dropout is basically what a dropout does is it removes certain nodes each time with a probability indicated here. So in this case, it removes a node from like the training on a specific image 1/5 of the time. And you don't really need to worry about this too much, but it basically allows all of the nodes to get trained more. So it makes it more accurate because all of the nodes get to see the data and like train it and have an equal focus. So this part of the code initializes the neural network model using these linear nodes. This first part shows how many nodes it takes in as input, and the second one shows how many nodes it outputs to. So you can notice we're chaining these different linear layers in order to actually get some hidden layers and make more accurate predictions using the model. So now this forward function is actually used to train the network. And so we start by flattening an image input. So this X parameter here is an image that has been taken in from the data set. So this flattening part sort of converts this image into a list of 28 times 28 or 784 numbers that can be more effectively processed by the neural network because they can be passed in as values into the first layer of the network. This part of the code just is how you actually connect the nodes together. Notice that there's f.relu, okay? Just like the sigmoid activation function that Joshua described, relu is another type of activation functions called a rectified linear unit, but sigmoid would work just fine here as well. So you can see this is how we connect them. Remember that the dropout layers sort of turn some of the nodes off on each training image in order to make all of the nodes be able to process that image good. And finally, we have log softmax, which is just used to format the output results into a way that we can see. So yeah, this is sort of the neural network that we created. So you can see it has 5 different layers. The first layer takes in 784 features, outputs 512. And then the bias is true, which means that it does include biases. It's not just weights, so that makes it more accurate. Second one takes in 512, outputs 256, and go, etc. down here until the last one outputs 10. Now there's also loss functions and optimizers that sort of help with the gradient descent part of the program. And they provide like the condition, they provide a value that, or like a function that you can actually conduct gradient descent on. And this optimization thing actually also does the gradient descent. So instead of like having to apply all the partial derivatives and stuff, PyTorch makes it really convenient to implement a machine learning model without having to write out a lot of code. So now we have training. You generally train models in units of time called epochs, and each epoch is one iteration over the entire training set. And you generally want to do like quite a few epochs because the more epochs you do, the more likely it is that you actually hit a local minimum in the gradient descent and do good in classification. Oh yeah, speaking of gradient descent and local minima, this right here is the learning rate. And the learning rate specifies the amount you actually move in the direction indicated by the gradient descent. And a larger learning rate makes it less likely that you get stuck in small local minima, but it also makes it more likely that you don't actually converge to a single minimum. So you want to generally get a good balance. Learning rates are between 0 and 1. You generally want to keep it on the order of 0.01, like 10 to the negative third. So this bit of code just basically trains the model on the data set. This torch.device, device, it says like if a GPU is actually available, then it uses the GPU to train the model much faster, but you don't actually need GPUs to train these machine learning models. It only makes it run faster. So if the CUDA GPU is not available, then it just uses the normal CPU. Model.to just moves the model to whatever device is specified by this. And then finally, model.train makes the model ready to be trained. So this for loop just makes the model go over the entire data set for epoch the number of epochs that we specified, which in this case is 30. So the loss function is just an indication of the accuracy of the model. The lower the loss is, the more accurate the model is. And you can use different types of loss, but again, that's a bit out of the scope. Then here, this train loader function was defined earlier to be the training set. So you just iterate through all of the data and target inside of that training loader. So all of this stuff basically just trains the model on the data set and optimizes it by changing the weights and biases of the nodes. And you can see here, I've already trained this model before, so you can see the output. You can see that as more and more epochs are run, the loss decreases as the model gets more accurate. And also notice how at some steps, the loss actually increases. So for example, between epoch 7 and 8, the loss jumps by 0.05, and that's just gradient descent it's just like the impact of the learning rate on how the gradient descent works. Now, finally, we can test this train data by basically doing the same thing we did to train it, except using model.eval instead of model.train, which preps it for evaluation. And then you just iterate through all of the test data and print out the loss and the accuracy. So you can see here that the test loss is 0.272, which is higher than the training loss because the model hasn't actually seen any of the testing data before. So we can't expect it to be as accurate as it was on the training set, but it was still pretty accurate. And you can see here, I've actually split the accuracy into different categories of the digits. And you can see that it's more accurate on some digits than others, which might be more recognizable. Like for example, it's more accurate on zeros because zeros are very different from other numbers, but it's a bit less accurate on twos because twos can look like other numbers. But overall, it's still really accurate as well, which is nice. Finally, here, this is just some code that visualizes the results of a sample test. So if you run this, it takes one batch of the images and it actually runs the model on each of those 20 images in the batch and it produces an output result. So you can see here the images in the batch show the image as well as what the model classified it as, which is outside the parentheses, and what the actual thing is, which is inside the parentheses. So you can see for this batch, it actually classified all of the numbers correctly, which is pretty cool. Let me see if I can fetch one that doesn't. I think it's all the same, but yeah, if there was one that didn't work, it'd be red here. So yeah, that's pretty much it. Does anyone have any questions about this network?
Yeah, definitely. Yeah. So I know that you guys might we cover a lot of information today, and I know that you guys might want to reference it back. I know we're recording this, but if you guys want, we can post all these material and lecture slides in the machine learning workshop channel on Discord. So yeah, we'll be probably posting that in that channel so you guys can access.
All right.
All right, I guess it is almost 4 o'clock. Okay, we have a question in the chat. Computer science math courses or skills do you think would be important? Yeah, so I would say that depends, since I guess in a sense that if you want to do machine learning and a lot do the models, you don't really actually need to know like for example, like what I went over, right? Like actually the math or actually how exactly it works behind it. Most of the times you can just kind of call this package or library and it kind of just does it for you. But if you're talking about like actually like fully understanding how the algorithm and like the math work, yeah, I would say, yeah, Vishnu, that is a good answer. I would recommend you first learn calculus. And I know there are some parts of multivariable calculus, but it's not that too much. And yeah, especially in machine learning, there'll be a lot of topics well, you'll be, or instances where you'll be actually using matrices and that kind of stuff. So that'll be important for you to learn. And as for, I guess, machine learning in general, I would recommend the Coursera classes, if you guys can search it up. Yeah, machine learning. I know that, I forgot exactly who the guy, okay, I think it's Andrew N. Yeah, Andrew N. His courses are pretty good and are a good start to get more in depth on machine learning, definitely. I guess Vishnu can respond there, but for me, I guess was actually, I guess I kind of started with the theory side of machine learning. So my first project was my housing price linear regression one. It gave me kind of a, get me familiar with Python and especially those packages and kind of stuff, and also maybe understand the algorithm a little bit better. So yeah, my project was actually, building the math and everything behind it, not just calling the function. But yeah, feel free to, yeah.
Yeah. I guess I didn't really like do any full scale projects like based on the math. I just coded some of like the functions. I guess my first project was probably the MNIST one, but like the first one I really did like without too much help was I actually created a really interesting classifier for heart arrhythmias. So like basically it took in data from electrocardiograms or just like, the beeping things or like the heart rate monitors that you can see sometimes in like medical TV shows and stuff. It just basically took in that as data and it was actually able to classify different types of heart arrhythmias or like irregularities in the beating of one's heart by looking at the data. So that was a really fun project. It taught me a lot about different types of machine learning models. And yeah, it was really fun. So I'd highly suggest you to find something that you're interested in. And after learning a bit more about machine learning, try creating a model for it.
Yeah, definitely. I feel like machine learning is one of those fields that are really like new in the sense that it's getting popular now, but I know that it's kind of hard to start off somewhere in machine learning. There's like so many different algorithms and topics, and everything like requires a lot of like background knowledge. So yeah, for me, I guess I would recommend some Coursera courses to get you guys started on the right path, and hopefully you can improve from there. Yeah. So are there any other questions? You guys are also free to ask the questions on Discord. We'll be answering it throughout this event. So yeah, if there are not any questions, I would like to thank all of you guys for coming today and staying for the full hour. That's a lot of dedication, and hopefully you learned something from this. I know that we covered a lot of pretty difficult and rigorous material, but I hope that you'll be able to actually use this in the future or throughout the EcoHacks event. So yeah, thank you guys for coming. We'll see you next time. Bye-bye, guys.
Yeah, bye everyone. Thanks for listening.